Hello everyone, welcome to the end of Unit 2 and Activity 13 with Lesson 13.3. We're going to talk a little bit more about rational functions and their features and also solving rational inequalities. So if we look here on page 176 today, we're going to see that we can have a variety of answers possible here, but we want to write the function a function that has a slant asymptote here at 2 minus 3x, and then a vertical asymptote here at x equals 1. So we can write this kind of in its most general state that we talked about in the last lesson, with that slant asymptote having 2 minus 3x here, and then just plus some value over x minus 1. Because we talked about it, it doesn't really matter what this value of a is. It's just some constant where it's not equaling 0. So where a is a constant that does not equal 0. So it won't kind of cancel out. So we see here, this could be 1, this could be 2, this could be a million, this could be -3, -4, just some kind of constant value that's not 0 to cancel it out. And you see the slant and the vertical asymptote there. Now we also talked about holes last lesson. So if we're going to have a hole, we want to think about having a function where that whole value would cancel out in the numerator and the denominator would cause that hole. So I don't know, we can make the other piece of this then just x plus 1 because we want something to be left over when it doesn't cancel out. So if we kind of expanded this out, an example then of a function that would have a hole would be this function right here. Okay. Now if we have something that has an asymptote that is x plus 3, and again vertical asymptotes that are plus or minus 3, again we want to think about having x plus 3 with our slant asymptote piece of this, and then we know we're going to have to add to it then. Again, just think about a being some constant. We would want x plus 3 and x minus 3 in the denominator. Now you could also rewrite that so that you had this as the more simplified version, x squared minus 9. That could also work. And again, this a value is just some constant here as well. Okay, so you see kind of the gist of these functions here with that notation. Now, a reminder with slant asymptotes or oblique asymptotes, kind of interchangeably used. If they're not giving it to you in the pretty format that we have here, you just need to use synthetic division in order to find that correct format. So in this case, our vertical asymptote would be at -4, so that's the value that we're going to use in the box. And then to find this simplified value here, we would use synthetic division. And what we would then find is, in this case, we would have y equals 1x minus 1 plus 2 divided by the x plus 4, since that was our remainder there. So that our slant asymptote would be at y equals x minus 1, and that vertical asymptote then again is at x equals -4. Okay, so we have it back in that format we are more used to. Now, the other big piece of information, besides reviewing some of the stuff we talked about last lesson that we need to talk about then today, is the idea of finding rational inequalities. And this is on page 177. And very similar to finding polynomial inequalities, we want to look at some key points. So some of the things we need to look at is we want to make sure we start with factoring your numerator and your denominator. And the reason being, we're looking for a couple of key features here when we factor the numerator and the denominator. You're looking for zeros, like we did with polynomial inequalities, but we're also looking for any of our discontinuities as well. So holes and vertical asymptotes. Those are all going to be key pieces we need for our graphs. And then from there, very similar to what we did with the polynomial inequalities, we are going to plot on a number line, and we're going to test the intervals to find our answers, okay? Just as we did with the polynomial inequalities as well, we're going to check where is it above or below the x-axis, where is it positive values, where is it negative values, and finally, you're going to write the solution in interval notation. So be careful of where we're using parentheses versus brackets, open circles versus closed in circles. All of that'll be included in this, just like it was with polynomial inequalities. So here's an example that they have here. And again, notice here they solved and found, in this case, some of the zeros, holes, and vertical asymptotes. When something is a hole, again, it's not a vertical asymptote, and vice versa. Something important to notice that they talk about kind of in here, but not super crazy, is the idea that our holes in our vertical asymptotes are always not included. Okay, what that means is they're either always an open circle or they're always involving parentheses, because we can't include a hole or a vertical asymptote because they are undefined points. Zeros are again going to be dependent on the fact, is this a greater than or less than sign, to see if they're included or not. So on your graph, in this case, they were all open circles because we weren't including zero, but be aware as we go through these examples, sometimes you might have closed circles and open circles all involved here, okay? So for this first example that we're going to look at, what we want to do is, again, we want to start by making sure we factor this completely. So the numerator can be factored to be x minus 5 and x plus 3. And then the denominator is already basically factored for us with x minus 4. So notice here we do not have any holes, nothing canceled out. What we do have is a vertical asymptote at x equals 4 when we set the numerator equal to 0. And then we have two different zeros. We have one at x equals 5 and one at x equals negative 3 from when we set the numerator equal to 0. So we're going to plot all three of those values on our number line. So negative 3, 4, and 5. And notice here the zeros will be closed in because there's an or equals to. So at 5 and negative 3, these are closed in. Open circle, though, always at the vertical asymptote. Right? They're always not included. Now, when we test our interval values here, if I pick a very, very negative number, like negative 100, I would have a negative times a negative divided by a negative. So a negative times a negative is positive, but divided by a negative value is going to overall be negative. If I pick a value between negative 3 and 4, so let's say 0, I would have a negative times a positive divided by a negative, though. So that would actually end up being a positive value. Next, between 4 and 5, if I picked 4.5, for instance, 4.5 minus 5 is negative, 4.5 plus 3 is positive, 4.5 minus 4 is positive. So this positive divided by a positive is positive, but we still have that negative there. And then last but not least, if we test a really, really large value in here, let's say 100, it's positive, positive, positive. For an overall answer, it's positive. Okay. So what we see is where these values are less than or equal to 0 would be where we have the negative signs, where things are y values end up being negative. So these two intervals here, which would be from negative infinity until negative 3, bracket, because this was included, this 0, or from our vertical asymptote to 5, notice the use of parenthesis here and then bracket here because it was not included and then included. So looking at one last example of this then on the part B, if we factor this one, we have x minus 3 and x plus 3. So again, none of these are canceling, so we don't have a hole. What we do have are two vertical asymptotes at x equals 3 and negative 3, and a 0, this time at x equals 1. So on our number line, we're going to plot these values. And they're all open circle this time because even the 0 is not included, right? And vertical asymptotes are never included. This time when we plug in values, let's say a very negative number, we get negative, negative, and then negative solution. So this overall is negative. And then we have a value between negative 3 and 1 is like 0. So we end up again with a negative divided by a negative times positive. So this is positive. A number between 1 and 3, like 2. This is positive, negative, positive. So a positive divided by a negative and a positive overall ends up being negative. And then a large number will create all positives to be a positive solution. So from -3 to 1 is where this is greater than 0, and from 3 to infinity is where this is greater than 0. So we finally have a solution of -3 to 1 and 3 to infinity. So again, looking at these graphs, we could always double check this on a graph as well to see, when we're looking at our graphs, where is this above the x-axis? So keep in mind we have that ability as well to look at our calculators. Last piece of this then, thanks for following along, and congratulations on making it to the end of Unit 2.